Good morning, everyone. I'm ITRI Max, the virtual host of this event for the Industrial Technology Research Institute. Today, I am honored to introduce the insights shared by Dr. Chiou Kuo-Chan, the Deputy General Director of our Material and Chemical Research Laboratories. Dr. Chiou will discuss our latest advancements in net zero carbon emissions technology and circular economy applications in the field of materials. At the same time, we hope to use this opportunity to recruit passionate individuals to join our research and development team, driving technological innovation and industry upgrades together. Let us contribute to the future of green technology and sustainable development. Are you ready? Let's get started.
Good morning, everyone. I am Chiou, the Deputy General Director of the Material and Chemical Research Laboratories at ITRI. Today, I would like to share with you our current materials development and circular economy applications related to net zero carbon emissions in the field of materials. The Material and Chemical Research Laboratories, or MCL, was established as part of ITRI in 1973. MCL itself was founded in 1982, followed by the establishment of the Chemical Engineering Division a year later. Due to the close relationship between materials and chemical engineering, the Material Research Labs and Union Chemical Labs were merged into one in 2006. Over time, we also incorporated groups focusing on water technology, nanotechnology, green circular materials, and precision engineering. The primary role of MCL within ITRI is the development of basic materials, which supports various departments within ITRI, including mechanical systems, optoelectronic systems, biomedical systems, communication systems, and green energy systems. Additionally, we address industry demands through cross-disciplinary collaborations, including smart manufacturing and cloud computing. We also engage in significant collaborations with the industrial sector. We also have some projects commissioned by the government to work with international universities. Given the wide scope of the materials field, MCL is organized into 14 groups covering electronic materials, metal materials, structural materials for nuclear applications, organic optoelectronics, energy materials such as batteries and solar cells, high-temperature materials, petrochemical materials, and applied chemistry. We also develop materials for major domestic industries such as semiconductor and liquid crystal display industries. We have groups focusing on fibers and textiles, ceramics, and water treatment technologies, emphasizing water recycling to support domestic industries. MCL currently has about 1,300 employees and holds around 6,000 patents. Through technological development, we have established 21 startup companies. Among our members, 28% have a doctoral degree and 55% have a master's degree, with over 83% holding advanced degrees. Our team primarily consists of professionals in chemistry and chemical engineering, followed by those in materials science. We also have experts in engineering, electrical engineering, mechanical engineering, biomedical fields, and physics. The experience distribution among our personnel is roughly 1/3 with over 20 years of experience, 1/3 in mid-level management, and 1/3 new staff. MCL's technological development is a microcosm of Taiwan's industrial progress. In the 1980s, we developed composite materials such as carbon fiber composites for bicycles, tennis rackets, and golf clubs used by companies like Giant. In the 1990s, we focused on passive components, solar modules, and LED materials. In the 2000s, we developed display materials for the IC industry. In the 2010s, we began developing high-frequency and high communication materials, such as those for 5G. We also developed water treatment technologies to assist the semiconductor and IC industries in recycling, as well as circular plastic materials. In recent years, we have expanded into circular economy initiatives, including net zero carbon technologies, low carbon materials, and CO2 absorption and utilization technologies. Our funding sources are approximately 40% from government funds for technology foresight research and 60% from industry collaborations. Our development focus spans four main areas: next-generation ICT materials, high-quality chemicals, green energy materials, and sustainable recycling technologies. Regarding international regulations for low-carbon emissions, many countries have set standards for 2030, aiming for net zero carbon by 2050. In this context, Taiwan plays an important role as an international supplier. In response to the demands of companies like Apple, which aim for 100% carbon neutrality by 2030, and brands like Nike and IKEA, which are gradually using recycled materials, we are developing corresponding technologies. Companies like Microsoft, Google, and Facebook also aim for 100% carbon neutrality by 2030. Taiwan's supply chain must develop technologies to meet these brands' requirements. Therefore, in this section, we look at Taiwan's export-oriented industries, such as semiconductors, panels, plastics, rubber products, printed circuit boards, and automotive parts. These technologies account for a significant proportion. So, how to reduce carbon emissions and enable recycling is an important technological challenge and goal. From a materials perspective, the two major sources of carbon emissions mentioned earlier are steel production and petrochemicals, which are our largest sources of carbon emissions. Additionally, our key industries include semiconductors, PCBs, displays, plastics, and textiles. Currently, Taiwan leads the world in the production of semiconductors and PCBs, and 70% of global textile production comes from Taiwanese manufacturers. Therefore, reducing carbon emissions and improving materials are crucial to achieving net zero carbon emissions. To define net zero carbon emissions, we must understand the concept of Scope 1, Scope 2, and Scope 3 as per ISO 14064-2018. Scope 1 covers direct emissions, for example, emissions from boilers and vehicles directly produced by the company. Scope 2 includes indirect emissions, for example, emissions from purchased electricity or energy used for heating and cooling processes. Scope 3 encompasses other indirect emissions, for example, all indirect emissions that occur in the value chain of the company, including upstream and downstream emissions. Considering these aspects, developing technologies to reduce carbon emissions across the entire value chain is crucial. Next, I will introduce how we are developing new low-carbon materials to replace traditional petrochemical materials in the petrochemical, electrochemical, and other chemical industries. New materials can be recycled and reused. For example, PET plastics, typically disposed of through thermal cracking process, can be recycled and purified for reuse, reducing the need for raw material processing or refining. Additionally, CCU, carbon capture and utilization, involves converting CO2 into chemical products through catalytic and purification techniques. We are also developing technologies for biomass materials and their applications, such as dyes and alternative raw materials, with some examples to follow. We are working on recycling PET fabrics and using them in new products. Through decolorizing, purifying, and recrystallizing processes, we can produce recycled PET that replaces traditional petrochemical PET. This process significantly reduces carbon emissions, achieving over 60% reduction, and allows for the production of wearable PET fibers from waste materials. We also focus on recycling plastics. Traditionally, waste plastics are incinerated as fuel. Through pyrolysis, we can convert plastics into high molecular weight liquids, which, after hydrogenation, produce chemical substances similar to naphtha and traditional olefins, for example, ethylene, propylene, butadiene. The gas byproducts can be reused as fuel. Additionally, during the flue gas emission process, such as coal-fired power generation, a large amount of CO2 is produced. We have partnered with Thai Power at the Taichung Power Plant to capture this CO2 and convert it into methanol using catalytic technology. Methanol can then be used as fuel. Compared to Japan and France, our process temperature can be redesigned to achieve better conversion at lower temperatures, resulting in higher recycling efficiency and achieving carbon reduction goals. Another major source of carbon emissions is the steel industry. Therefore, we have collaborated with China Steel Corporation. During the steelmaking process, CO2 emissions are captured using pressure swing adsorption, PSA, which produces high purity hydrogen and CO2. Through chemical reactions, these can be converted into methane, ethane, and even propane. During this process, the captured CO2 is purified to obtain high-purity CO2, which is then combined with hydrogen production technologies. Currently, hydrogen is produced through water electrolysis and other methods. This high-purity hydrogen and CO2 can be converted into methane, which can be used as fuel. We have established an experimental line in collaboration with China Steel Corporation within the plant to verify this technology and achieve recycling. This is an example of our integration of technologies with steel and chemical industries. We also use CO2 in chemical reactions to produce PU, polyurethane materials. Due to the healthy and environment issues associated with isocyanate, which is a controlled substance, developing sustainable and non-isocyanate PU, NIPU materials will be very important. By capturing CO2 and reacting it with epoxy, we can produce cyclic carbonate compounds, which is a material for NIPU production. We collaborate with domestic companies to apply these PU materials in synthetic PU, leather, foam materials, and coatings. Additionally, the captured CO2 can be used to react with alcohols to produce polycarbonate diol, PCDL. We work with polymer companies to produce related products. As mentioned earlier, CO2 capture and utilization requires hydrogen. We also have hydrogen production technology. We have developed related proton exchange membrane, PEM, for hydrogen production. Hydrogen can be utilized to produce chemicals through reaction processes with CO2, and another part can be used in hydrogen fuel cells to support fuel cell applications. Apart from current electric vehicles, Japan is developing hydrogen-powered vehicles and hydrogen-powered drones. These technologies can replace existing battery applications to achieving hydrogen energy society. In addition to these efforts, we have also developed related chemicals. For example, the production of denim requires extensive use of dyes. These dyes are predominantly derived from petrochemical processes and require large amounts of water for dyeing, including soaking and washing, making it a highly water-intensive industry. Therefore, we have adopted a biological reaction method using E. coli to synthesize biodyes through biochemical reactions of the bacterial strain. These dyes do not require large amounts of water for biodyeing processes, making the indigo dye outcome exceptionally beautiful. We have also applied these dyes to commonly used products such as backpacks and pencil cases, replacing traditional chemical dyes to achieve water-saving and environmentally friendly effects through this biotechnological approach. Currently, we have produced related products within our institute for internal personnel to test and evaluate the technology and industry viability. Moving forward, we will collaborate with both domestic and international companies. Additionally, as mentioned earlier, carbon reduction is not limited to petrochemical industries. We are also exploring the technology to obtain related chemicals from bio-based materials. Starting with fructose, we dehydrate and oxidize it to produce polyester materials like FDCA, which can then react to form polyesters such as PEF, replacing traditional petrochemical PET. These materials can be applied in daily life products such as water bottles, bio-based fibers, and transparent PET moldings. We have already used this bio-based PET to make sneakers and have had our colleagues test these fully bio-based PET sneakers to evaluate their durability and performance. We have also developed materials related to home care applications. These materials include not only organic materials, but also some crystalline materials and organic functional materials. We develop relevant composite materials used in various products, such as lightweight materials needed in the aerospace industry and composite structural materials required in nuclear power plants. Furthermore, there are significant ICT products in the domestic market, including 5G products and chemical semiconductor materials, optoelectronic materials, and so on, required for electric vehicles. We also have job openings related to material simulation. We welcome individuals interested in research and development to join the chemical industry. This concludes my introduction and sharing. Thank you.
Thank you all for your participation today. We hope that through today's introduction, you have gained a deeper understanding of ITRI and the Material and Chemical Research Laboratories. We look forward to the opportunity to collaborate with you and drive the advancement of Taiwan's industries together. If you are interested in joining ITRI, please click the recruitment link below and fill in your information. We look forward to meeting you.